Okay, so hi everyone and welcome to the ICTS String seminar. So today we're very happy to have Julius Julius. We'll talk about bootstrapability.
Yes.
Right.
Thank you. Let's check that this stuff works. All right, perfect. Hello, I'm audible online as well. Okay, perfect. Thank you very much for giving me the opportunity to present some of my work. So today I'll be telling you about a program of research which we started about a year ago, which we call Bootstrability. And before I start, I want to also acknowledge my collaborators. So some of them may be joining online. There's Nikolai Gromov, Andrea Cavaglia, Michelangelo Preti, and Nika Sokolova. All 5 of us are from King's College. Andrea recently moved to Turin. So we started this program about 1 year ago, and I want to tell you more about it. So let's start by thinking about what it means to solve a conformal field theory. Okay, in practice, we can say I have solved a conformal field theory if I know what's called the CFT data to any precision at any value of the parameters of the theory. And what is the CFT data? The CFT data is the spectrum of all primary operators in the theory and the structure constants of all 3-point functions of primary operators. So in my language, solving a CFT corresponds to knowing the CFT data exactly for any values of the parameters of the theory. Now, having this as a setup, you can ask the next question. Suppose there is a CFT, in this case, an integrable CFT, where I know the spectrum, right? Suppose I know the spectrum of the CFT, then can I ask the following question? Can I just, knowing the spectrum in spectral information, if I'm able to implement crossing symmetry as well, does this in some way imply the structure constants as well? So in the particular case that we are studying, if we consider 4D planar n equals to 4 supersymmetric angles theory, in the planar limit, this theory is integrable. And we know, therefore, at least in principle, we know the entire planar spectrum of this theory. Crossing symmetry can be implemented using the conformal bootstrap. So the question that we're asking is, does it make sense to combine conformal bootstrap with integrability? That's how we get the name Bootstrability. So that's this is the question which I'm going to pose to you now. Hopefully, by the end of my talk, you will be at least somewhat convinced somewhat convinced that it might not be a completely wrong thing to do. All right, so let me start by just reviewing how integrability works, how integrability techniques work to solve the spectral problem for n equals 4 supersymmetric angles theory. I'll give you a very, very basic example and then that will try to illustrate how this thing works. Okay, so let's start with the spectral problem in n equals 4 super Yang-Mills. And actually, let's just go to weak coupling. And I just want to remind you of a very important paper written by Minahan and Zarembo back in 2002. So they were working at weak coupling and they were considering the following. They were considering just correlation functions, 2-point functions of traces of scalars in n equals 4 super Yang-Mills. And what they observed was that the mixing matrix of a trace of L scalars at one loop can actually be mapped to the Hamiltonian of a closed length L SO6 integrable spin chain. And the mapping is very precise in the sense that the mixing matrix the one loop mixing matrix gets mapped to the Hamiltonian. The trace of the L operator's trace is just implemented by closed boundary conditions in the spin chain. L operators inside the trace goes to length L of the spin chain, and the scalars themselves that are living inside this trace, they become spins in the spin chain. And when you have this mapping, what happens is that the energy spectrum of this Hamiltonian then actually just gives you the spectrum of anomalous dimensions of these single trace operators. So at one loop, this is what Minahan and Zarembo observed. Turns out that not this exact mapping, but integrability techniques can be used even non-perturbatively. And starting with this, I'll just try to explain briefly how that works. So let's again stay at one loop and let's even further restrict ourselves. So let's actually, instead of using all 6 scalars, let's restrict to 2 complex scalars. So just 2 complex scalars in n equals 4 super Yang-Mills. In this case, you don't have an SO6 integrable spin chain at one loop. You have an SU2 integrable Heisenberg spin chain at one loop. And as you can see here, because it's at one loop, you have this factor of 2g square, where g is just the Hooft coupling, rescaled in a way which is popular in our field. The length L over here corresponds to L sides of the spin chain, as I said, which correspond to L operators inside the trace. Here we have the identity operator, and here we have the permutation operator. So this is the Hamiltonian. What the identity operator does is absolutely nothing. And what the permutation operator does is it flips the spins at two sides in the spin chain. All right, so then, as I was saying in the previous slide, you have this kind of mapping. Suppose you have some operator, which is a trace of some x's and z's. This can be mapped to a state in this Hilbert space with some spins up and spins down. All right, so once you have this setup, you can ask, okay, how do I find the energy spectrum? So let's consider the eigenstates of this Hamiltonian. The ground state is particularly easy. If I have all my spins facing down, for example, then the action of the identity and permutation just cancel each other, right? Because permuting everything down, you'll just get the same thing. So they cancel each other. And therefore, my ground state, for example, can be just all spins down. You can ask the next question, okay, how do I get excited states? You might say, okay, maybe an excited state is all spins are down, except one spin going up. So something like, if you forget this part, if you just say this. But here you see a state with only a single spin flipped up, can't really be an eigenstate of the Hamiltonian because the permutation operator will flip these two spins. So while the identity doesn't do anything, so Hamiltonian acting on this doesn't really, it's not an eigenstate. The way to go around that is actually to define this state, which is a state called, this is a state which is called a single Magnon state. So what you do is you flip one spin up at each position. So I've actually not written this very well, but here this is the ith spin which is flipped up. So you flip up the ith spin, multiply by some factor e to the ip1, and then you sum over all i's. So you flip one spin up, then multiply by this phase factor, flip this next spin up, multiply by phase factor, and add all of them up. And this is actually a legitimate eigenstate of the Hamiltonian. And it's the eigenstate, obviously, it's not an eigenstate for any value of the Hamiltonian. It's an eigenstate for a particular value of P, which is called the Magnon momentum. And to find what the Magnon momentum is, what you should do is you plug this into the Schrodinger equation and then try to solve for P. And if you do that, and you also do it for a state with n magnons. So I showed you here just a single Magnon state. However, I can have multi-Magnon states as well. Each Magnon is associated with some Magnon momentum. And therefore, and then if you have an n Magnon state, in general, you can find that the energy of the state is given by this formula where Pi are the different Magnon momenta. Again, I notice another typo here in the equation. This should be L. I'm sorry about that. All right. So as I said, here you have n1 magnons in this in this particular state. All right. So as I mentioned briefly, that in order to get the Magnon momenta, you need to actually solve the Schrodinger equation. Now, when you solve the Schrodinger equation, what happens is actually it takes the form, the allowed Magnon momenta can be rewritten in a form of in some equations known as the Bethe-Ansatz equations. And the Bethe-Ansatz equations, essentially, the solutions of the Bethe-Ansatz equations give you the Magnon momenta, which will go into your energy formula. Of course, I was using P for Magnon momenta, but here I have U. And that's actually just because we in order to write the equations look a bit better if you change from the Magnon momentum P to what's called a spectral parameter U. But nevertheless, you can write the same equations in P's as well. Furthermore, I introduced some notation here, which just says that when I do plus plus in front of a function, all I mean is that I have this function, but it is not evaluated at u. It's evaluated at u plus I, and this function is evaluated at u minus I. That's all it means. And these Qs themselves are what are called Baxter polynomials. And what the Baxter polynomials contain are just U minus Ui, where Ui are the roots of this equation. Okay, these are the roots of the equation. They are called the Bethe roots. And they, using the formula which I showed you previously, can be converted to Magnon momenta. So the Bethe roots are the same thing as the Magnon momenta. And if you know the Bethe roots, you therefore know the energy. So so you can find the energy spectrum of this SU2 spin chain by solving the Bethe-Ansatz equations. No, you obtain it from the Schrodinger. So you say that you ask for your eigenstate to be an eigenstate. You ask for your eigenstate to be an eigenstate of the Hamiltonian, and then from there you can derive the Bethe-Ansatz equation. All right. Another thing to notice is that actually it's a good point, because I'll make a comment right now, related to what you said, which is another thing to notice is that actually the Q1, it also solves what's called a Baxter equation, which is just a finite difference equation, which looks like this. And this actually, if you see, it's very similar to the Bethe-Ansatz equations. And over here, T of U is called T of U is a polynomial which is just fixed by self-consistency of the Baxter equation. But the point which I wanted to make here was very similar to the question which you just raised, is that actually the Baxter equation is kind of the analog of the Schrodinger equation for this case. And in keeping with this analogy, what you get is that the Baxter polynomial is analogous. So the Baxter polynomial Q, which I showed here, is kind of analogous to a wave function. Why did I make this statement? I made this statement because of the fact that this is a second order equation, but I showed you only one solution. And actually, it's true that the Baxter equation has two solutions. And the way to see that is by noticing the following ambiguity. So I told you last slide that the ground state of this Hamiltonian is all spins facing all spins down. However, an equally valid ground state would be all spins pointing up. And these two are completely equivalent, right? So basically, if I have n1 spin-ups in an n1 spin-up excitations in a completely spin-down vacuum, this is completely equivalent to saying I have n2, which is L minus n1 spin-down excitations in a spin-up vacuum. And what this means is that actually I can define another Baxter polynomial, Q2, which has the asymptotics u to the power n2. Notice that here, the asymptotics of this Baxter polynomial is u to the n1, where n1 is the number of magnons. I can define another Baxter polynomial Q2 with asymptotics u to the n2, which also describes the same system. And this is actually a second solution to this Baxter equation. Q1 and Q2, in fact, are also independent solutions, linearly independent solutions to the Baxter equation. And this means that, well, in differential equations, if you have independent solutions, then you have a non-zero Wronskian. For finite difference equations as well, there's a notion of a discrete Wronskian which you can define. I'll comment on that in a second. There's a notion of a discrete Wronskian which you can define. And what this just means is that the linear independence of the Baxter polynomials implies that this Wronskian, is non-zero. And in particular, this Wronskian is just proportional to u to the L in this case. Okay, so before I continue on this point, let me just mention earlier, I reiterate earlier that you can see that the charges of the state, in some sense, the number of magnons, they actually live in the asymptotics of the Baxter polynomials. And this is an important point. All right, so so the linear independence implies that we have this Wronskian, and then this is the Wronskian relation, which just says Q1 and Q2 arranged in this determinant form are actually just proportional to u to the power L, where L is the length of your spin chain. Now, so this is basically just a quick review of how the Bethe-Ansatz works at one loop for the SU2 spin chain. But the reason why I did this was actually to tell you about the philosophy which we are going to use. And the point is the following, that actually these QQ relations, so this Wronskian relation is a simplest example of what is called a QQ relation. A QQ relation is just a relation between different Baxter polynomials. They can actually be used if you define, well, this is an auxiliary comment actually, but anyway, I started making it, I will make it. You can have, you can actually use these relations to derive this Baxter equation itself. All right. Okay, so let's go to the next slide. So basically, the whole point of the recap previously was to make the following statement, that the Bethe-Ansatz equations, which I showed you, are actually completely equivalent to the following three things. The Bethe-Ansatz equations are completely equivalent to knowing the asymptotics of Q1 and Q2, knowing that they are polynomials, and knowing the fact that they have some Wronskian relation or some determinant form relation between them. So the point is that the Bethe-Ansatz equations are completely equivalent to knowing this asymptotics, the asymptotics, polynomiality, and knowing these functional relations. Now, Bethe-Ansatz equations in general, they are very good. They are very useful to solve what are called highest weight spin chains, where you can define some kind of ground state and then build all other states by starting with this ground state. But then if you look at n equals 4 super Yang-Mills or integrability in n equals 4 super Yang-Mills, for example, you actually don't always have highest weight spin chains. You also have non-highest weight spin chains where Bethe-Ansatz techniques don't necessarily work. However, the Bethe-Ansatz technique, the Bethe-Ansatz, as I said, is completely captured. So is completely implied by knowing the asymptotics, polynomiality, and the Q and the QQ relations. So what this means actually is that you don't need the Bethe-Ansatz equation. You just start with your QQ relations, which are some algebraic relations. You say that these determinant relations are solved by some Baxter polynomials, which I know whose asymptotics I know, and whose and also I know that they are polynomials, and this actually is completely equivalent to the Bethe-Ansatz equations. But this philosophy is useful even in the case where you don't have highest weight spin chains. So this flow of logic is the logic of the quantum spectral curve, and the quantum spectral curve is the quantum spectral curve is one of the most sophisticated techniques to solve the spectral problem non-perturbatively in n equals 4 super Yang-Mills theory. And the point which I wanted to make here is basically that so all you need are these Q functions. All you need are these QQ relations and some assumptions about asymptotics and polynomiality, and this actually is equivalent to the Bethe-Ansatz equations and actually can go beyond them. So let me just review quickly what is the quantum spectral curve for planar n equals 4 super Yang-Mills. We don't actually have SU2 anymore. SU2 is only when you have X's and Z's. We actually have the full symmetry group PSU2, 2/4. So what this means is that instead of having 2 square Baxter polynomials, I actually have 2 to the 8 Baxter polynomials. You may say, I showed you only 2 Baxter polynomials. How are there 4? Actually, there is also a trivial Baxter polynomial, which is 1, and also u to the power L can be considered a Baxter polynomial. So you actually have 4 Baxter polynomials in the SU2 case, and in the PSU2 2,4 case, you have 2 to the power 8 Baxter polynomials. Again, so the Wronskian relation is a special case of a QQ relation, but there are many, many more QQ relations for PSU2 2,4, and actually you don't need 2 to the 8 Baxter polynomials. All you need are 8 polynomials called PA and QI, and these are sufficient to determine all 256. Furthermore,
so 8 comes from the rank plus 1 or something?
No, it's just rank, right? I mean,
right.
Yeah.
So the rank, no, I thought the rank is less.
Sorry, yeah, rank plus 1. Yeah.
So, but PSU, there are 2 U1s that you divide by.
Yes.
So I would have thought it's.
Okay, yeah. So this is a good question. So the point is that at the level of QQ relations, actually all you need is SU4/4. So the QQ system is the same as you'll have for SU4/4, but this extra PSU stuff, this actually gives you some additional kind of relations. There's some notion of Hodge duality which comes in. So you have some upper index and lower index functions, and they are related in a particular way. And this, so this is reflected over there. Yeah, it's a good. Yeah, I smudged over that point, but yeah, that's from QQ relation point of view, it's as good as SU4/4. That's why we have this 8. And these 8 distinguished polynomials are called P1, P2, P3, P4, Q1, Q2, Q3, Q4. Again, whatever I said previously was only at one loop, but this integrability thing holds non-perturbatively as well. And what this means is that I don't have backstep polynomials anymore. I have Q functions. This can also be seen from the fact that you don't have highest weight spin chains anymore. If you have highest weight spin chain, then you can always have polynomials, backstep polynomials. But then once you have non-highest weight spin chains, you don't have polynomials anymore. You have Q functions. And the polynomiality, which I was talking about before, this just gets changed into an analyticity. So what this means is you impose some particular analytic properties of these PA and QI. And what exactly are these properties? The properties are that PA, the 4 PA, P1, P2, P3, P4, they just have one branch cut in their in the plane of the spectral parameter between -2G and 2G, where G is the rescaled at Hooft coupling. And the QI also have, well, the PA have a sheet where they have only one branch cut. And also the QI have a sheet where they have only one branch cut. Also between -2G and 2G, but the branch cut is through infinity. Yeah, in a way, you can think about P's being associated with S5 and Q's being associated with ADS5. Yeah, which is also why the cut is kind of compact cut in one case and non-compact in the other. All right, so this is just a lightning review of the quantum spectral curve. To solve the spectral problem in n equals 4 super Yang-Mills. So you can use this technology to find the planar spectrum, to find the full planar spectrum of n equals 4 super Yang-Mills. So you can take any single trace operator, and in principle, you can find its scaling dimension for any value of the Hooft coupling. I mean, you have to, it takes a lot of implementation, but it can be done in principle. Now that I have, let me just check, have a look. Okay, good. So now let me describe in particular the setup which we work in. And the setup which we work in is actually a one-dimensional defect CFT, which lives inside n equals 4 super Yang-Mills. And it's defined in the following way. So we consider a half BPS Maldacena-Wilson line and planar n equals 4 super Yang-Mills. So what does this mean? You have a usual Wilson line in n equals 4 super Yang-Mills, but what makes it a half BPS Maldacena-Wilson line is that you include, along with the usual coupling to the gluon, you also include a coupling to one out of the 6 real scalars in n equals 4 super Yang-Mills. And this is just an infinite line going from -infinity to +infinity, you just have an infinite line. And actually, this infinite line, half BPS Maldacena-Wilson line, can actually be thought of as a defect CFT itself. What that means, what I mean by that statement is the following, that I can define such correlation functions, some double bracketed correlation functions of operator insertions on the line. So what do? I start at -infinity, I go till the point T1. At T1, I insert an operator O1, and then I go from T1 to T2, insert O2 at T2, all the way till I insert On, and then I continue the line to +infinity. And this observable basically satisfies, so it was shown by these authors that this observable satisfies all the axioms of a 1D CFT. And you can actually think about just this observable being an endpoint function in a one-dimensional CFT. So that's the setup in which I'm going to work. All right. So let me just speak a bit more about the symmetries preserved by the line. So usual n equals 4 super Yang-Mills, you have some 4D conformal symmetry, bosonic symmetry times SO6R symmetry. Now, presence of the line, what happens is that the 4D conformal symmetry gets broken into a 1D conformal symmetry along the line itself, times physical rotations of the line. We can do an SO3 around the line. And because I chose one out of the 6 scalars, which I call phi parallel, to be coupled to the line, I break SO6 to SO5. Now, because the symmetries are broken in this way, states in the CFT, in the defect CFT, are labeled by the following quantum numbers. you have delta associated with SO1, 2. S is associated with SO3. And R1 and R2 are Dinkin labels, if you want, associated with SO5. All right, so these are the states and they're labeled by these quantum numbers. And as this is not just a conformal defect CFT, it's actually a defect super conformal field theory. And that's why there are two types of states. Essentially, you have short operators, so protected short operators, whose dimension is protected, so it's integer or half integer. And you have unprotected long operators whose dimension is in general a non-trivial function of their Hooft coupling. And in general, we don't, so the quantum spectral curve basically developed for the defect CFT can in principle find for you delta, I mean, numerically at least, it can find for you delta at any value of G for any choice of these quantum numbers. In principle, it can do it. In practice right now, at the current stage, at today's stage, we can do it for any value of R1 and R2, but the spin is equal to 0. But it's more of a sit and implemented problem to make it work for arbitrary spin rather than a conceptual issue. So yeah, so these are the states in the CFT. So let me describe the observable which we will study. The observable which we will study is this particular 4-point function. Now this 4-point function is a 4-point function of four scalars, but these scalars are different from the ones which couple to the line. So, well, phi1 is just a choice of scalar polarization, and this orthogonal just tells that it is orthogonal to phi parallel. So I have 6 scalars in n equals 4 super Yang-Mills. I choose one phi parallel couplet to the line. Now I have a space of 5 scalars, and I choose one of them. Okay, and I choose one of them, and I construct a 4-point function out of these scalars. I should also mention, well, I'll mention in a moment. So yeah, so this is the main observable which we will study. It's also the 4-point function which we will bootstrap in the future. And this, okay, I have this notation to show it. So you just have this line, and then you have 1, 1, 1, 1 at 4 points. This is just some notation. And yes, so since this is a 4-point function in a conformal field theory, by conformal symmetry, you can write it as an arbitrary function of the cross ratio times some kinematical part. Now, because we're in one dimension, there's only one cross ratio, so I can write it as an arbitrary function of x, where x is the one-dimensional conformal cross ratio. Furthermore, these phi perpendiculars, as I call them, they are part of a short displacement multiplet in the defect CFT. So in other words, insertion of phi perpendicular on the Wilson line can also be thought of as an infinitesimal change of the path of the Wilson line as well. So that's why they're called displacement operators. Well, yeah, and this is also displacement operator. So the point of this is just that it has protected dimension 1. So that's why I just have square over there. All right, so this is the observable which we study. So as I said, you can write it as an arbitrary function G of the 1D conformal cross ratio. And then what you can do is, because it's a super conformal CFT, you can do also super conformal OPE. And that was done by these authors here. And they managed to write down it in the following way. So they managed to write G of X after doing super conformal OPE in the following way. Now let me explain what this is. F over here is a known function of G. It's a known function of G. It's actually related to the expectation value of just the circular half PPS line, which was computed by localization, but also we showed recently that you can reproduce the same. You can calculate F purely using integrability, purely using integrability results. D is a known differential operator, again, found by these authors, and it acts on this function F. And F, you can actually write a super conformal operator product expansion of it. And it has 3 different types of terms. The first terms is just X, which can be thought of as the conformal block of the identity. The second term is C square short times F short. So the C square short and F here, they are related to each other. Like 1 plus C square is F. And this is completely known. We can calculate it completely from using integrability results already. F short, so these are just super conformal blocks, and they are known hypergeometric functions, again calculated by these authors. And finally, we have the sum over here over delta I. So let me tell you what those delta I are. These delta I are super primaries of long multiplets with very specific choice of quantum numbers, and basically that they are chargeless, so they don't have any kind of spin SO3, or they don't have any SO5 charge. And the scaling dimension of these operators is known from integrability. So using the quantum spectral curve modified for the 1D CFT, you can actually find the spectrum of any operator with these quantum numbers. And the point of saying all of this is that actually the only thing which is unknown is these OP coefficients or structure constants that are exchanged here. And this is the only unknown in this entire expression. And these are the targets of the bootstrability approach.
The first term that you said,
yes,
no, the that one there, that's, you said the half BPS.
Yeah,
Wilson loop expectation.
it's related to it. It's not exactly that.
So that was like the usual one.
This Bessel function. Yeah.
So it's just a function of the coupling.
Yes, exactly. Completely known. We know what it is. Yeah, it was calculated first using localization, but then we managed to.
Oh, that times x square.
That times x square. Yes. It's not a function of x square. Yeah, it's a function of g times x square. Yes.
And you said this capital this early dx is also known.
It's a known differential operator, which was I mean, its form is known. It's just a differential operator whose form is known by, was derived by these people. Yeah. So everything is known here except the C's. Everything was known except deltas and C's. Now we know deltas, so everything is known except for C's. So I claim that I know the deltas. So let me show you. So these are this is the spectrum. Well, it's not the full spectrum. It's the spectrum of the lowest 10 states of a long multiplet with these quantum numbers. This was obtained using the quantum spectral curve. And then just I label the states according to in which order they appear at weak coupling, because you see there are some crossings and stuff. So we just label them at weak coupling, but it doesn't matter. We know I'm only showing you 10 states here, but we know 35 states with these quantum numbers. And basically the spectrum gets more and more dense as you increase delta, as expected. And the spectrum gets more and more dense as you increase delta. So at delta equal to 4, actually it's a huge mess. So you can actually see, we have in our paper we have a plot with that as well. So it's a huge mess of states and they're crossing and all of that. And also another comment which I can make is that the spectrum at weak coupling is complete up till delta equal to 6. At delta equal to 6, you can do a counting of states using characters, etc. And until delta equal to 3, it's definitely complete. At delta equal to 4, using QSC, we have 19 states, but we're not totally sure how complete it is yet. But again, it's a technical question more than a conceptual thing. So we should be able to clarify that. And at strong coupling, this plot is complete until delta equal to 7, but actually if you use all 35 states, which we know even delta equal to 8, we have the complete spectrum at strong coupling as well. So yeah, so this is the spectrum of these states.
Is there a degeneracy at large lambda?
Yes. So in fact, there's a degeneracy. There's a degeneracy not just at leading, it's leading and subleading order. So all of these all these states have this.
So what is it that's giving the degeneracy of strong coupling? Is it
so I don't know. I don't really know the answer to the question, but I know that Meneghelli and Ferrero have the answer to that question. So in their paper from last year, they said it's just group theory. By group theory, they can just show you that even the slope of the states is just comes from each of the states will have the same slope as well. But I don't know more deeply why they become degenerate. Yeah, so all of them, they are going to integers, and they go to integers at strong coupling, and their slope is the same. So these two states, they have the same slope. These four states have the same slope, etc., etc. All right.
I have a nice question.
Yes.
So here you have all the phi's aligned along a certain line, right?
Yes.
But in a generic situation, they can be all over the place, right?
No, but I'm restricting the phi's to be on the line.
Yeah, I mean, when you're talking about solving for the CFT, shouldn't you be considering all possible positions?
On the line, because I'm
no, not on the line. Not on the line. I mean, in the whole space, in the whole hexadimensional space.
No, but I'm in a one. So I have my Wilson line, right? And
so
I have
this. In case of a Wilson line, I understand. But
okay,
in general, operators, phi of x1, phi of x2, phi of x3.
Sure.
x1, x2, x3 could be anywhere, not along a certain line.
Sure. In general, yes.
Yeah. So I mean, so this is a restricted consideration you're doing, right?
Sure. Yes, definitely. I'm restricting myself to the one-dimensional CFT. I will make some comments about local operators towards the end, but right now I restrict myself to the. I should look at the camera actually. Right now I restrict myself to the 1D CFT. Thank you. Yeah. All right. So this is the spectrum. So let's try to bootstrap it, right? We did the integrability. Let's do the bootstrap part. So we're going to implement bootstrap using semi-definite programming. So in order to bootstrap, you need crossing symmetry. So where is the crossing coming here? So the crossing comes in the following way. So if I have this line with S1, S2, S3, S4, but actually the line is equivalent to the circle. So I can make a circle, and then I can open the circle again. So S1, S2, S3, S4 is equivalent to S4, S1, S2, S3. So this is the crossing symmetry. And using that, you can actually write a crossing equation in terms of F. And this is the conformal bootstrap equation. So this is the crossing equation which we are going to solve using the bootstrap. Now, this I've just introduced some notation over here. So I define this calligraphic G as just the crossing symmetric. So this is the crossing equation. I write it as calligraphic G. And then what you can do is then you can actually expand calligraphic G in terms of the same superconformal blocks as I described before. So you have this G1, you have C square short times G short plus C I squared times G delta I. Again, the sum over delta I, we know delta I, we know G, we know G short, we know C square short, we know G1. The only thing which is unknown is Ci squared.
Excuse me, maybe a very basic question. Can you just say how crossing symmetry implies that, if it's like easy to explain? Or
I can't tell you right now.
Okay,
no.
that's
Okay, so how do we implement the bootstrap? We do it in the following way. So what we do is we take the known parts, we put it together, and we call it G known. Now, right now, we fix a structure constant which we want to study. So in this case, it is C square 1. So this corresponds to the 3-point function of two external phi perpendiculars and the lowest dimension phi parallel, the lowest dimension chargeless operator exchange in the OPE. So that's the 3-point function whose structure constant I want. And I write it in the following way. I say, let there be some spectral gap at delta equal to 2. All this means is that I have G known, I have this C square 1, which I want to calculate, plus everything else is put on the side. And then this we want to bootstrap this crossing equation. So the way we do it is by using these functionals, but let me just make a comment before that. The comment is just that the crossing equation is nothing but an infinite set of linear equation for an infinite number of variables. And one way, for example, to solve such an equation would be just take random values of the cross ratio, sample this equation at random values of cross ratio. Then you have, for example, let's take n different values. So you have n different equations for n different structure constants, and then you can try to solve for them by doing that. For example, we're not going to do that. The point is just that functionals are just a more sophisticated and actually more industrialized in some way method which has been developed by many authors over the past years to solve this kind of equations. So the way we do it is the following: you define you look for two functionals, alpha plus and alpha minus, and these functionals are nothing but some coefficients alpha plus or minus j times the 2jth derivative, and you have a sum from j is equal to 0 to some number of derivatives n derivatives, and the precision of the conformal bootstrap is actually controlled by the number of derivatives. So we define functionals like this, and we are looking for functionals alpha plus and alpha minus which have the following. On the state which we want to study. So for the particular structure constant which we want to study, I want alpha plus minus to be plus or minus 1. Then above the gap, so in the previous case I said from delta 2 onwards I set the gap. So above the gap I want the functional acting on g delta, where delta is greater than the gap. I just want it to be greater than 0. And finally I want to maximize the value of the functional on the known parts. Okay, so these are the three. So I look in the space of functionals for a functional which has these three properties, and once a functional which has these three properties basically will then, if you plug this back into your crossing equation, it will put bounds on c square 1 in the following way, right? Because the functional acting on the crossing equation, it will give 1 over here, it will give something greater than 0 when it acts on the stuff above the gap, and it is maximized on the known part. So you can therefore, by finding these two functionals alpha plus and alpha minus, you can actually put a bound on c square 1. And these alpha plus or minus L, so these coefficients, they're optimized using the HTPB implementation of the conformal bootstrap, developed, I guess, developed by all of these authors. And as I commented previously, the precision control is achieved by controlling number of derivatives. So if you have more derivatives, in principle, you should get more precision. So
I have a conceptual question. Could you go back to the previous slide, please?
Yes.
So in this circle, the understanding is that you have exchanges between, say, S1, S2, and S4, S3 in the T channel, and S1, S4, and S2, S3 in the S channel. Is that correct?
Yes.
So that means that the operators which in the middle of the diagram, which join the S channels and the T channels, those are outside the lines, right? I mean, because those operators, they sit outside the lines, Wilson lines.
So
right?
Maybe let's leave that for the discussion at the end because time is running out.
Okay, so I have 15 more minutes.
Yes, 15 minutes.
Okay, yeah, okay, let's we'll get back to that at the end. But actually, that's a good point because I saw the watch. I also need to move a bit faster. So let me show you preliminary results now. So yes, so just by using just two states, I showed you 10 states in the spectrum. Just by using the first two states in the spectrum, and just by using the first two states in the spectrum and doing this bootstrap, we managed to get this plot. And this plot, we managed to get this plot for this structure constant c square 1. And let me explain this plot. So on the y-axis, I have c square 1, and on the x-axis, I have g, which is the three-scale Hooft coupling. Just to comment, g equal to 4. Already the Hooft coupling lambda is in the thousands. It's already like 2000 or something. So I go from lambda equal to 0 to lambda equal to 2. So it's truly non-perturbative and really goes from weak to strong coupling. And this blue line is the result which you get. And this blue line is actually not a line. It's actually the difference between the upper bound and the lower bound. So as you can see, just injecting these two states is extremely restrictive for the conformal bootstrap because it gives you such small bounds on the structure constant that it almost just looks like a line. Also, I want to comment that at weak coupling, we know the same structure constant up to order g to the power 10. And at strong coupling, also it is known in 1 over lambda up to 4 orders at strong coupling by Meneghelli-Ferrero. And yeah, and so we are able to get non-perturbative bounds. And yeah, the fact that we're able to really access this non-perturbative region of the Hooft coupling for a non-spectral observable is quite, I mean, this is, it's not very often where you can do this. And so we're quite proud that we were able to do that. But then can we do better? Turns out that we can. Naively, there's already one thing. I show you, you can tell me, oh, you showed me 10 states, but you used only 2. Can you use more states? And the answer to that is yes. So one can set the spectral gap to a higher state. Let's call it delta n, where n is greater than 2. And suppose actually we're interested in finding the bounds not for C1, but some other Cm, where m is between 1 and n minus 1. Essentially the same procedure which we did works, just we need to do one extra thing. So we are again looking for the same functionals. Same functional acting on the particular state which we want should give plus or minus 1. Sorry about that. It should be greater than 0 after the gap. That's also fine. The only extra thing which we impose is that at the particular states which we know, we want the function to be above 0. We let it be negative between the states, but at those states we want it to be greater than 0. And then we maximize it on the known part. And this actually is quite useful. So then again we get the same kind of bounds. So why does doing this help? Doing this helps because including higher states actually allows us to search in a higher space of functionals. And that's because, as I said, we allow the function to be negative. So in the case where I had only 2 states, you see that this functional has to be above 0 after delta 2. But then if we actually include 10 states and force the functional to be greater than 0 only at the states themselves, it's able to access this area as well, and that actually helps it. Another way to improve is by using integral constraints. And so this is actually a way to get more input from integrability. So in view of time, let me quickly go through how this is. So the way to understand this is actually not to study the Wilson line, but to study a slightly different observable. It's not very different. What you do is you have the same Wilson line with phi parallel as the scalar polarization. But then after a point, you change the scalar polarization slightly by introducing a small angle theta in R space. Now this change in scalar polarization, as I said earlier, can be, this change in scalar polarization, what it does, it gives you kind of a cusp in R space. And this cusp line in R space can actually be resummed. It can be written as just the straight line plus an insertion of displacement operators integrated over the line times sine square theta. So you insert 2 displacement operators times sine square theta. You insert 4 displacement operators times sine to the 4 theta. You actually have also some other contributions at sine to the power 4 theta. And you can actually expand this in order by order in theta. Now, 2 comments here. The first comment is that this 4-point function is exactly the same 4-point function which we studied before. The second comment I'll make in a second. If you go back to this cusp line, actually the expectation value of the cusp line can also be expanded in theta. And at order sine square theta, it's actually the Brent-Strahlung function, which is already known from integrability. At order sine to the power 4 theta, you get Brent-Strahlung contribution and something called a curvature function, also known from integrability. And in principle, it is known to, so that my second comment is, in principle, it is known to all orders in theta. The expectation value of the cusp line in principle is known to all orders in theta. Just we have nice analytical form at these only for these 2 orders, but again, it's a technical question to go higher. So yes, so again, here we have something which is completely known from integrability, which can be related to the observable which we are studying. And indeed, what you can do is you can use this setup to obtain 2 integral constraints for the 4-point function, and those 2 integral constraints are presented here. And one way of, so these integral constraints, well, you might ask, why do I have 2 integral constraints with 1 deformation? The answer is that I showed you deformation in R space, but I can make the same deformation in physical space. I can have a physical angle phi. So you can do both of these deformations, so you get 2 integral constraints, and they are written here. Now, these integral constraints can actually be thought of as crossing symmetric independent functionals acting on the 4-point function as well. So they can further be used to constrain the 4-point function. And that's precisely what we do. Another comment is that actually these two, what I've presented here just for simplicity, is up to regularization. So there are some infinities which show up, but we know how to regularize everything. And yeah, so one combination of these integral constraints was actually, after we wrote our paper, it was derived by these authors. And in an upcoming work, we have some steps of a derivation for another combination of them. However, we have checked that these things they work for 4 orders at strong coupling and 4 orders at weak coupling. So we are very sure that, and also actually non-perturbatively numerically they are working. So we are very sure that they are correct. So yes, so we have extra spectral information as well as integral constraints. So we can combine everything together, and let's see how our results improve. So this was the result which I showed you. 2 states, no integral constraints. Now what we do, let's take this point here. So actually, let me comment a bit over here. Basically, at this point, we had only around 2 digits precision at this point. But let's take a point here. Maybe we had 3 or 4 digits last year when we wrote this paper. Let's zoom it by 25 times, and then let's zoom it by 25 times again. Then we see this green line. This green line is what happens when you get 10 states and 1 integral constraint. But then if you zoom the green line again, you see that there's a red line. And what's the red line? The red line is what you get when you have 10 states and 2 integral constraints. So when you have 10 states and 2 integral constraints at a completely arbitrary finite value of the coupling, we are able to get 7 digits of precision for the structure constant, which is a non-supersymmetric structure constant, non-protected long version in some way of a structure constant. And that's basically our main flagship result. We can actually also get higher structure constants. So even for C2 and C3, we can get some bounds. However, as I briefly mentioned earlier, the spectral density is much less at strong coupling than at weak coupling. So actually the bootstrap works better at stronger coupling, and with stronger coupling, we have much better bounds. At weak coupling, the states start to merge with each other at weak coupling. Well, so I mean, at weak coupling, it's a bit harder just because the spectrum is much more dense. And because, but then we think that the way to go forward is to study multiple correlation functions and stuff like this. And so these are our numerical results. We can actually also get perturbative results analytically. I won't explain how it's done. Very briefly, I can tell you it's you make the basis of HPLs, and then you impose log cancellation, inject spectral information, crossing symmetry, and then you try to extract weak coupling data. So the same C²1 we know up till order G to the 8. We know until order G to the 8. C2 and C3. So the next 2 structure constants we know up to 1 loop. Further structure constants as well we know up to 1 loop. Higher structure constants are known until tree level, and the entire 4-point function up to 2 loops we know it at 2 loops. So I can actually show you. The 1 loop was calculated by these 2 authors in 2018. So we managed to get 2 loops, and the 2 loop result, the second loop term is given here, where these H's are defined in the following way. So H2, which is H01, is just Li2. H10 is this, and then using this recursion relation, you can build up all the other H's. But essentially, we know analytically what this thing is at 2 loops as well. So yes, in the last 5 minutes, I will talk about future directions. All right. So the first immediate future direction is to bootstrap multiple correlation functions, and the inspiration from this can be thought of. Inspiration for this comes, for example, from the Ising model. So for the Ising model, when they did the first bootstrap stuff, they only bootstrap 1 correlator, and they found this kink in the allowed region, and they said, does the Ising model live there? Does it not? They were not sure. And then eventually, once they studied more correlators, I think they study a family of 3 correlators here, they were really able to make this into a really small island. Already with 1 correlator, actually, we have more precision than they did for a non-spectrum observable, because they have 5 digits and we have 7 digits for structure constant. But nevertheless, it seems like the right can we go in this direction? So this question can be rephrased in two different ways. You can say, can bootstrability reproduce a number? Can I inject spectral? Is the same question which I asked at the starting. Does the spectrum define the CFT completely with crossing information? In other words, with crossing symmetry. In other words, it's a question my friend Maxime asked me once. He said, can you hear the shape of a drum, right? If I play you the spectrum of a membrane, can you reconstruct the shape of the membrane from that? So so that's what it would mean if you can know a CFT completely from its spectrum, for example. So anyway, so as I said, we bootstrapped only one correlator and we found remarkably good bounds. However, with one correlator, we don't expect that the bounds can shrink to 0, simply because you should not be able to just know the from the spectrum, be able to construct everything about the CFT. Of course, integral constraints in this way can be thought of like hearing the shape of the drum and then also the deformed drum, and using this extra information you can probably reconstruct, but without anything it should not be possible with only one correlator. However, if we study multiple correlators, we do expect that we should be able to push precision much further. And also a good part is that potentially infinite number of correlators are there to be studied with this way. And this is work in progress with the collaborators who I mentioned at the start of the talk. Yeah, so the last concluding, I have 2 slides left just with some conclusions about other observables. So I should comment that we study a true beyond the spectrum observable in planar n equals 4 super Yang-Mills. In a sense, actually, it's also really complicated observable, because even though we restrict to 1D, so we reduce the amount of symmetry, the number of states which we have is still the same as we have in 4D. So in some sense, it is harder. Also, we have only 1 cross ratio. In 4D, you have 2 cross ratios. So in some sense, it is a harder problem, but it's a truly planar problem. So it is kind of a good observable to study. Nevertheless, there are other observables which you can study. You can look at what are called G functions, which is a 1-point function of an operator in presence of a defect, in this case, a Wilson line, but it can be any other kind of defect as well. You can construct Wilson loops with funky shapes and different cusps and try to find the correlation function of multiple cusps. And finally, you can think about correlation functions of local operators in n equals 4 super Yang-Mills. Now, I'll just comment a few things about the last thing, and then I'll stop. So let's think about bootstrability for local operators in n equals 4 super Yang-Mills. In some sense, actually, the moment you know the planar spectrum, you have solved the problem of multiple higher point correlation functions as well in the planar limit, simply because of large n factorization. Nevertheless, if you want to get some information about 4-point functions, non-trivial information about 4-point functions, you actually need to go to the next order in 1 over n expansion. And what this means is that double traces enter the game, and double traces is something which, at least in integrability, we don't have very sophisticated techniques yet to deal with. So this is something which we need to think about. So I just have a picture here which describes exactly the same thing. I won't go through it because I don't have time, but it's exactly the same thing. If you have 4-point function of 4 operators at leading order, of course, everything factorizes, but at subleading order, you can exchange a double trace with an O1 structure constant, or you can exchange a single trace with an O1 over n square structure constant. So both of them contribute at the same order. So it is a problem which we can think about. And there are some open-ended ideas about this. This is my last slide. So recently, the group at McGill came up with a very interesting way to deal with this. They understood how to project out double traces by having a very clever choice of functionals. So they choose functionals in a way that the double traces vanish. But the drawback about this method, naively at least, is that these functionals which they need, they are trigonometric. And as a result of that, they are oscillatory. They don't decay at infinity. And this might actually be a problem with precision. So when you want to numerically implement, you might not be able to get the precision which you need. So that's a direction in which one can think. It's a very nice direction which they started, but this is a place where we can think about trying to improve it. Another direction was recently done by the group at Oxford, and what they did was they related the 4-point function of 420 bar operators in n equals 4 to graviton scattering amplitude in field theory, in string theory, and what they managed to do was they were able to actually write an equation which only involves single trace spectrum and structure constants, and just using symmetry they were able to extract the strong coupling spectrum of the Konishi operator, for example. Now this is very good because strong coupling spectrum of Konishi, or spectrum in any case of single trace operators, is very well understood with integrability, so it might be a way as well. The only drawback probably in this case is that they are able to do it only at strong coupling. So it's an open question to generalize it to finite coupling. Okay, so with this I will stop. So thank you everyone for the attention. Thank you.
Okay, thank you for the talk. Are there any questions?
So sorry,
Yeah.
you come up in the double trace
because there's only one trace. Everything lives inside the Wilson loop, right? So if we go, it'll take a few seconds to go back, but you see exactly. Yeah, you see everything. Oh, everything lives inside this trace. So I have one trace in all of these operators, and these operators are adjoint valued, right? So there's only, yeah, that's why. And that's why this is actually a proper planar observable.
And one more question. Does this sort of operator and geofence that you are computing, is it amenable to this hexagon sort of approach?
In very, very good question. But so you're speaking about hexagons in 1D.
Yeah, I mean, people.
Yeah, it's true.
Only want to apply it to local operators.
Yeah.
I don't know whether they have the generalized to this sort of situation.
To be very honest, I'm not very sure, but I think the answer could be probably yes, because the one loop was computed in a paper of Komatsu, and I have not read that paper very well, so I don't know. But one of the section titles in that paper is hexagonalization of the. So there might be something, but I honestly don't know myself. But I don't see anything that prevents that from happening.
How did people? You showed up to 4 loops or something for some.
For the first structure, for C1 square, yeah. For this one.
So how did people compute this?
So no, we computed this. So the way you do it is you make a basis of HPLs, of harmonic polylogs. You assume the structure constant has this form with some uniform transcendentality at each order. Yeah, exactly. And then you plug that into the crossing equation. Then you inject spectral information, you expand your integral relations at weak coupling as well. And then you solve for the coefficients of the HPLs. So you get some equations with some constraints and you solve for them. And yeah, so actually going beyond G to the 8 here, so G to the 10, we have more, we don't have as many constraints as coefficients, so we can't go much further. That's actually another reason, another thing which is telling us to study multi-correlators. If you study more correlators, it's probably possible. Yeah. And also for the full 4-point function at 3 loops, we can't do for the same reason. Yeah.
Any other question? Maybe online?
Yes, I have a question.
Yes.
The thing is, it's related to the thing that I was asking before. In general, when you have all the 4 operators on the line,
yes,
then what happens is that the vertices at which the S and the T channels operate, those vertices are outside the line. Is that correct? I mean, they can be outside the line. There's no problem with that. But what I'm concerned about is that the extra direction, the extra direction is the radial direction. Isn't that correct? The Wilson line.
I get your question. I don't think that the vertices. Wait. Actually, no, I don't get your question. Which vertices are you speaking about?
The vertices that form the SNT channels. I mean, the intermediate vertices.
Yes.
Those are outside the line. They have to be outside the line, because if you draw the circle, and then if you draw the SNT channels coming from the 4 vertices, then in general, the intermediate vertices will be outside the Wilson, the circle that you have drawn. So in general, when you're considering the line picture.
Okay, I see your point. I'm not totally sure how to answer your question right now, but
no. My question is, like, isn't that extra space curved because it's the radial direction, right?
Yeah. So
no, this in general, that would mean that they're really Witten diagrams instead of normal.
Yeah. No. I get what you're saying. I'm also Michelangelo. I think you're also in the audience. If you have some comments at this point, please feel free to make them. But let me just try to think right now. I don't have an answer for you right now, but let me just think. Let me think for a second. No, in general, basically this 1D CFT is you can forget that you are you're on a defect in 4 dimensions. You can completely forget and treat it as completely as a 1D problem, and you can very consistently define everything. So I'm very sure that what you're raising as a concern is not a concern. However, I don't know how to convince you right now. What I can say is it is definitely a very well-defined 1-dimensional problem. And yeah, it is a well-defined 1-dimensional problem, but exactly how to convince you, I'm not quite sure right now, unfortunately. Sorry.
Any more questions? Okay. If not, let's all thank the speaker again.
Thank you. Thank you.